Hello everyone. This note set is going to be about orbital hybridization, orbital overlap diagrams, and then sigma and pi bonds. So first things first, I just want to talk about why orbitals hybridize in the first place and why we care. Okay, so you've looked at orbitals through the lens of single atoms so far. So we've looked at a configuration of any particular atom, carbon, hydrogen, oxygen, whatever, and you have generated a code that tells you where that atom's electrons are hanging out at any given time, right? We've done the code, the electron configuration. We've done orbital diagrams where you did your upward and downward spins on those electrons, and we've modeled those configurations with balloons so far. So you have an idea of what those orbital spaces look like in 3D. But again, we've only ever looked at them through the lens of single atoms. Now we're going to look at them through the lens of atoms that are trying to bond with one another. And when atoms bond with one another, their orbital spaces tend to hybridize. And the reason that that happens is because when atoms are bonding, they are minimizing the amount of potential energy between them to create the most stable state possible. And when orbitals hybridize, that minimizes the potential energy of those electrons, all right? And what it also allows them to do is bond more times than you would traditionally think they would based on their orbital diagrams of atoms in just by themselves, okay? And I'll show you what that means going forward. So the first thing I want to do now is just talk about some of the different shapes and patterns that you might see for hybridization. So if you look on your VSEPR chart that I gave you and you find molecular geometry, you find a linear molecule, you find tetrahedral, you find trigonoplanar or trigonal pyramid or whatever, and you look in that row all the way to the right-hand side, you're going to see hybridization patterns like these, okay? And the hybridization pattern tells you specifically what kind of orbitals are hybridizing and how many of each kind of orbital is hybridizing. So for a linear molecule, something that is sp hybridized, what that's telling you is that an s and a p orbital space are smashing themselves together, and instead of being spherical and then that funky little water balloon shape, they're going to create a shape that's a little bit different. It's a hybrid of those two. Okay, and I don't want you to think that it has to specifically be a 1s orbital or a 2s orbital and a 2p orbital. It could be any energy level you want. It could be a 3s and a 3p, a 4s and a 4p, a 5s and a 5p, literally anything, just one of the s's and one of the p's, okay? If something is sp2 hybridized, that means that an s and then two of the p orbital spaces will hybridize together and create a hybrid of them. And again, this could be a 2s and 2p's, or it could be a 3s with two of the 3p orbital spaces. It could be a 4s with two of the 4p orbital spaces. It could be any energy level, but this is telling you amounts. If you are sp3 hybridized, that's an s orbital, and all three of the p orbital spaces in any particular subshell are hybridizing. If you have an sp3d, that means an s, the 3p orbital spaces, and a d orbital space are hybridizing together. And then lastly, if you have an sp3d2, that means an s, three of the p's, and two of the d's are hybridizing together to create these shapes that you're seeing over there. Okay? So let's look at hybridization through the lens of the carbon atom, okay? So for carbon, let's just talk about its normal configuration. Carbon's normal configuration is 1s2, 2s2, 2p2. The 1s subshell is not included when we talk about orbital hybridization, and the reason for that is because the 1s subshell would house core electrons. And so we don't pay attention to those. What we want to know about are the valence electrons. And the reason we want to know about those is because The valence electrons are what are going to be participating in a bond, all right? So I'm just going to fill out that valence shell orbital diagram, or the arrow diagram, as you'll know it better. For those 2s, 2 electrons, here's our 2s subshell, and then for our 2p electrons, this would be 2px, 2py, and 2pz. And if you forgot what those x, y, and z monikers mean, it just means orientation in space. And so I have 2 electrons to distribute, so I'm going to put my 2 electrons in my 2px and my 2py, leaving my 2pz orbital space blank entirely. To give you a visual idea of what that looks like, this little sphere over here is going to represent my 2s subshell, and those 2 electrons are going to be chilling in that orbital space. This over here is going to represent my 3 possible p orbital spaces for my 2p subshell. So in my 2px orbital space, represented by this over here, I'm going to have an electron chilling in that space, and I'm going to have an electron chilling in my 2py orbital space. And again, this over here, the 2pz orbital space, is going to remain blank because I did not have an electron to put in it to begin with. So let me just sum up real quick. This is an unhybridized set of orbitals, and you should already be a little bit familiar with this. When those 2s and 2p orbital spaces start smashing themselves together, they can do that in different patterns. So my first pattern that I want to talk about is sp3 hybridization specifically, and that happens if carbon is forming 4 single bonds. Okay, so let's say carbon was participating in CH4 as a molecule. That means that it is single bonded to all of those hydrogens. And the preliminary Lewis structure would look like this. All right, when that happens, the 2s and all 3 of those 2p orbital spaces are going to smash themselves together and hybridize. Okay, so this downward spin electron that is paired up in that 2s subshell actually gets promoted up during that hybridization process and becomes an upward spin electron to occupy that 2pz space. Then the spaces smash themselves together and they create a new shape. And when that happens, you'll end up with an sp3 hybridization pattern, and all of those electrons will be unpaired now and available to form a bond. Okay, so visually what that looks like is you're no longer going to see separate orbital spaces like you're seeing there. Instead, you're going to see something like this. We have our carbon atom, and then we see 1, 2, 3, 4 orbital spaces, and your orbital spaces are going to look a little bit more spherical than P's traditionally look, but not perfectly spherical. And this 4th one I'm just going to draw as a dotted line because it's projecting backward in space. Okay, and so I count in my sp3 orbital diagram, I count 4 upward arrows. And so that means that I'm going to put 1 electron in each of those sp3 hybridized spaces. Okay? If we have sp2 hybridization, like we're seeing down on that 2nd row here, then that means that carbon is forming a double bond in 2 single bonds. So let me just really quickly give you an example of a molecule where you would see that. In the molecule CH2O, carbon forms a double bond with oxygen and 2 single bonds with hydrogen. So just draw out that Lewis structure for you real quick. It would look like that. So we can see that double bond forming here and then those 2 single bonds. All right. if carbon is hybridizing in that pattern, that sp2 hybridization, that means that the s orbital space, this one, and then 2 out of 3 of the p orbital spaces are going to smash themselves together after that one downward spin s electron gets promoted up. And so you end up with this. You get your sp2 hybridized orbital spaces, but you also have your p orbital space just kind of left out and unhybridized. Okay? So if I were to draw that out visually so you can see it, I'm once again going to put my carbon in the middle, and I'm going to put my 3 hybridized ones, but this time I have this P left out and it is unhybridized. Okay, so I'm going to draw that this way, and I'm going to attempt to draw it well enough to represent that difference in shape. All right, so that's our unhybridized P, that one in green. So when I distribute my electrons, I have to follow my orbital diagram again. I see that there are 3 electrons in my sp2 hybridized one, so that's going to be 1 each. 1, 2, 3. And then I have this electron that's chilling in the unhybridized p orbital space. So I'm going to put 1 in that space. Okay. Last but not least, we have sp hybridization. So that's the last one here at the bottom. And in that situation, carbon is forming a triple bond and 1 single bond. All right, so an example of a molecule where carbon would be hybridized like that would be in the molecule HCN, which looks like this. All right, so we can see that carbon is going to form that triple bond over here with nitrogen and a single bond with that hydrogen. Okay, in an sp hybridized pattern, what happens is we only get an s in 1 of the p orbitals that are going to smash together and hybridize. But 2 of the possible 3 p orbital spaces gets left out of that hybridization. So we get something that looks like this. Over here on the left, we have our sp hybridized orbital spaces, and over here on the right, we have 2 p orbital spaces that are left out and unhybridized. Okay, so let's draw that visually. I have my carbon atom in the middle, and I'm going to have my hybridized ones just kind of sticking out on either side. And then I'm going to have an unhybridized P. And let me switch colors for the other one. And then I have another unhybridized p orbital space. Okay, so if I look back at my orbital diagram, I see that in the sp hybridized space, there's 2 unpaired arrows, so I'm going to put 1 electron in each of those hybridized ones. And then if I look at my unhybridized orbital spaces, I see that in each of those p unhybridized spaces, I have an electron. So I'm going to put 1 here in the green one and 1 here in the pink one. Okay, so that is what it looks like visually. So this may not make a whole lot of sense to you right now, but I would like to stress that this is just another way to look at what is going on in a bond at any particular time. Okay, so I'm going to stop the video right there, and then I will create another video to talk about orbital overlap diagrams and sigma and pi bonds.